Hello there. Welcome to Info Jungle, a place where we slow things down. Let curiosity take its time. Explore the world without rushing past its quiet details. Wherever you are right now, settle in. Get comfortable. Let the noise of the day step back for a while. There is water moving right now, beneath several kilometers of ice. It flows in total darkness. No sunlight has touched its surface in 15 million years. The pressure above it could crush steel. The cold should freeze it solid. Yet it moves. This is not a small puddle trapped under snow. This is an ocean, larger than some seas you can name, hidden under the thickest ice sheet on Earth. For most of human history, we had no idea it existed. Antarctica looked like a dead continent from above, white in every direction, frozen solid to the core. Scientists assumed the ice went straight down to bedrock. They thought nothing could survive there. They were wrong. Beneath that frozen shell lies a liquid world. It connects lakes the size of cities. It carves rivers that stretch for hundreds of kilometers. And somehow, against every expectation, it contains life. The discovery changed everything. Everything we thought we knew about this planet. But it also raised questions. Questions that still keep researchers awake at night. Questions about what lives down there in that eternal darkness. Questions about how long it can stay sealed. Questions about what happens if that ancient water reaches the surface again. Because this ocean is not stable anymore. It is waking up. You can see it in the data streams. From instruments buried deep in the ice. You can hear it in the vibrations. Vibrations that echo through the glaciers. The system that held steady for millions of years is beginning to shift. Scientists call it the subglacial ocean. They study it with tools designed for space exploration. They drill through ice older than human civilization. They listen to frequencies that tell stories. Stories about water moving where water should not exist. What they find down there does not always make sense. They pull up samples containing microbes. Microbes unlike anything in our databases. They detect chemical signatures. Signatures that suggest processes we do not fully understand. They map channels and caverns. Channels that reshape themselves faster than the models predict. Every answer creates 3 new mysteries. This documentary will take you beneath the ice. Not with speculation or drama, but with patience. We will move slowly through the layers of discovery. We will look at what scientists have found and what still puzzles them. We will explore why this hidden ocean matters. Not just for Antarctica, but for every coastline on Earth. Not just for geology, but for the search for life beyond our planet. The ice above is 4 kilometers thick in some places. The ocean below has never seen the sky. Between them lies one of the deepest mysteries still waiting on Earth. And the remarkable thing is this. We barely know it is there. Most people have never heard of Lake Vostok. They do not know about the rivers flowing beneath the ice sheet. They have not seen the maps. Maps showing hundreds of buried lakes. Lakes connected like veins under skin. This world exists in darkness and silence. But it is not empty. It is not still. Something is happening down there right now. Water is circulating. Chemistry is unfolding. Life in forms we are only beginning to recognize persists. Persists in conditions that should make it impossible. The scientists who study this place describe a strange sensation. They stand on the surface in negative 40-degree cold. The wind batters their equipment. The horizon stretches white and endless. But they know something. That beneath their feet, separated by all that ice, there is liquid water. Ancient water. Water that remembers a time before ice covered this continent. Water that might hold answers. Answers about how life begins, and where else it might exist. That knowledge changes how they see the landscape. The ice is no longer just ice. It is a ceiling, a barrier between worlds. And that barrier is thinning. The warming planet is not just melting ice from above. It is changing the ocean currents. Currents that flow beneath the ice shelves. Warm water from the north is creeping under the frozen edges. It is melting the ice from below, where satellites cannot see it. This hidden melting accelerates everything. The glaciers lose their grip. They begin to slide faster toward the sea. The subglacial rivers swell with new meltwater. Lakes that have been isolated for millions of years start to connect, start to drain. The system is responding to changes. Changes it has not felt in a very long time. What happens next is uncertain. The models struggle to keep up with the complexity. Too many variables interact in ways that are difficult to predict. But one thing is clear. The ocean beneath Antarctica is not separate from our world. It is part of the same system. What happens down there will eventually affect what happens up here. Sea levels, ocean chemistry, climate patterns that shape weather across the entire planet. This is not a distant concern. It is already beginning. So we return to that opening image. Water flowing in darkness. An ocean sealed away. Sealed for longer than our species has existed. Moving now in ways it has not moved before. The ice above does not know what is happening below. It simply responds to the physics. Pressure and heat. Stress and flow. The ancient balance shifting into something new. This documentary will not tell you to be afraid. Fear is not useful here, but attention is, because the ocean beneath Antarctica remains unsolved. We do not know everything it contains. We do not know how fast it is changing. We do not know what signals it is sending. Signals about the planet's future. What we do know is this. It exists. It is vast. And it is waking up. If you enjoy these quiet explorations and want more spaces like this, spaces where the world moves a little slower, feel free to subscribe the channel and like the video, only if it feels right for you. Let us begin by understanding how we found it at all. For decades, Antarctica was a blank space on the map. Not because no one had been there, but because no one could see below the surface. Explorers crossed the ice in the early 20th century. They planted flags and measured temperatures, but they saw only what their eyes could reach. Ice and more ice, stretching to every horizon. The assumption was simple. Solid ice covered solid rock. The continent was frozen all the way through. Nothing could exist in that environment except cold. Then radar technology improved. In the 1960s and 70s, scientists began flying aircraft over Antarctica. They carried instruments that could send radio waves deep into the ice. These waves traveled downward. When they hit something, they bounced back. Most of the time, the signals returned exactly as expected. They showed layers of compressed snow turning to ice. They showed the gradual increase in density with depth. But in certain areas, something strange appeared on the readings. The radar waves were reflecting perfectly. Too perfectly. As if they were bouncing off a mirror instead of rock. At first, researchers dismissed these signals as errors. Equipment malfunctions. Interference from the ice itself. But the signals kept appearing. Always in the same locations. Always with that same perfect reflection. Someone suggested a possibility that seemed absurd. What if those reflections were not errors? What if they were hitting liquid water? The idea faced immediate skepticism. Water should not exist under that much ice. The weight alone should crush it. The cold should freeze it solid. But the physics told a different story. Under enough pressure, water behaves differently. Its freezing point drops. The weight of several kilometers of ice creates pressure. Pressure so intense that it actually keeps water liquid. Add a small amount of heat from the Earth's interior, and the base of the ice sheet becomes a zone where solid and liquid can coexist. Geothermal heat seeps upward from the planet's core. Just a tiny amount, a few fractions of a degree. But it is enough. Combined with the pressure from above, it creates conditions. Conditions where water can flow. The radar was not malfunctioning. It was detecting something real. Hidden beneath Antarctica's frozen surface were bodies of liquid water. Not small pockets. Not temporary melt pools. But massive lakes. Some of them hundreds of kilometers long. The discovery stunned the scientific community. It meant Antarctica was not a dead continent. It was a system, a hidden hydrology operating entirely out of sight. Researchers began mapping these signals more carefully. They flew grid patterns across the continent. They recorded every reflection. They built images of what lay beneath. The results revealed something extraordinary. Antarctica contained not just a few isolated lakes, but hundreds of them, connected by channels, linked by flowing water. It was an entire network. A subglacial ocean spread across the continent, spread like roots beneath a tree. One of these lakes became the focus of intense study. Scientists called it Lake Vostok. It sits beneath nearly 4 kilometers of ice in East Antarctica. Its surface area covers more than 14,000 square kilometers, roughly the size of Lake Ontario. But unlike any lake on the surface, Vostok has been sealed away. Sealed from the atmosphere for at least 15 million years. Maybe longer. That isolation made it irresistible to scientists. Because if water had been trapped that long, completely cut off, what might it contain? The theories ranged from fascinating to unsettling. Perhaps ancient microbes still survived down there. Perhaps the chemistry had evolved in unique ways. Perhaps the lake held clues about Earth's distant past. Or perhaps it held nothing at all. Just sterile water. Dark and empty. There was only one way to find out. Someone would have to drill down and take a sample. But that idea immediately created problems. How do you drill through 4 kilometers of ice without contaminating what you are trying to study? How do you ensure that modern bacteria from the surface do not fall into an ancient ecosystem? How do you even operate equipment in temperatures that make metal brittle, that make machinery fail? The technical challenges were enormous, but so was the potential reward. Access to a sealed environment, older than most species on Earth. Teams from multiple countries began working on the problem. Russians focused on Lake Vostok. Americans targeted other lakes in West Antarctica. Each group developed drilling techniques. Techniques meant to minimize contamination. The process was slow, painfully slow. Drills moved through ice at rates measured in meters per day. Each layer had to be analyzed, each depth recorded. And always there was the fear of ruining everything. One mistake could introduce modern microbes into a pristine environment. One contaminated sample could invalidate years of work. So they moved with extreme caution, sterilizing every tool, filtering every fluid, monitoring every temperature change. When the first drill finally approached the water layer beneath Lake Vostok, the team stopped. They did not puncture through immediately. Instead, they left the final meters untouched. They wanted to develop better techniques, cleaner methods. Meanwhile, other teams reached smaller lakes. Lake Willans, Lake Mercer. These were closer to the surface, easier to access. In 2013, a drilling team broke through into Lake Willans. The water that came up through their instruments was crystal clear, nearly free of particles. They collected samples and brought them back to the surface. Then they sealed the hole and waited for the analysis to reveal what 15 million years of isolation had created. The results came back within months, and they were astonishing. The water was not sterile. It contained life. Thousands of species of microorganisms, living, metabolizing, functioning in total darkness under crushing pressure. The discovery confirmed what many had suspected, but few had proven. Life does not need sunlight. It does not need warmth. It only needs liquid water and a source of energy. Beneath Antarctica, that energy comes from chemistry, from reactions between water and rock, from minerals dissolving and gases being released. The microbes down, they had learned to survive on almost nothing. They divided slowly. They used energy carefully, but they were undeniably alive. This changed the definition of where life could exist. If it could thrive beneath Antarctica's ice, then it could thrive beneath the ice of Europa, or Enceladus, or any frozen world with liquid water hidden inside. The subglacial ocean was not just a geological curiosity anymore. It was a window into the possibilities of life across the universe. But it also raised uncomfortable questions. What else was down there? How much did we still not know? And what would happen if the ice above began to melt faster than expected? Because once you discover a hidden ocean, you cannot pretend it does not matter, especially when that ocean is starting to move. Think about this for a moment. Right now, under the coldest place on Earth, there is water. Water warm enough to support life. Not just traces, not just potential, but actual living organisms. functioning, reproducing, existing in an environment that should be completely hostile to biology. By every reasonable measure, they have been there longer than modern humans have walked upright. They have survived ice ages. They have endured pressures that would collapse submarines. And we only just found them. That realization does something to your sense of scale. It reminds you how much of this planet remains unexplored. Not unexplored in distant jungles or deep oceans, but unexplored beneath ice we thought we understood. Antarctica is not the frozen wasteland we imagined. It is a living system, hidden from view, but active in ways we are only beginning to measure. The lakes are just the beginning. Beneath them run rivers, not frozen, not still, but flowing through channels carved into bedrock. These rivers connect distant parts of the continent. They carry water from the interior toward the coast. They move sediment and nutrients. They shape the landscape in darkness. And now they are changing, responding to warmth they have not felt in millennia. Scientists measure the flow rates. They watch the pressure readings. They listen to the ice shift and crack. Shift as water moves beneath it. The data tells a story. The subglacial ocean is not static. It breathes. It circulates. And recently, it has started to accelerate. What does that mean for the ice above? What does it mean for the coastlines thousands of kilometers away? What does it mean for the search for life on other worlds? These are not abstract questions anymore. They are immediate, urgent, because the ocean beneath Antarctica is waking up. And when it moves, the entire planet feels it. Let us go deeper, into the rivers that connect this hidden world, into the forces that keep it liquid, into the systems that scientists are racing to understand, before they change beyond recognition. The ice above may look eternal, but beneath it, time is accelerating. Water does not care about our assumptions. It follows physics, pressure, gravity, heat. When conditions allow it to flow, it flows. Beneath Antarctica, those conditions exist. Conditions scientists did not expect. The ice sheet is not a solid block resting on rock. It is a dynamic surface, moving, bending, responding to forces from above and below. At the base of the ice, where pressure peaks and geothermal heat rises, a thin film of water forms, sometimes just millimeters thick. But it is enough. That water does not stay in place. It migrates. It finds channels. It carves paths through the rock and along the underside of the ice. Over time, these paths become rivers. Not metaphorical ones. Actual rivers, flowing for hundreds of kilometers, carrying water from the heart of the continent toward the edges. Scientists discovered these rivers by accident. They were studying how glaciers move. They noticed that some glaciers slid faster than others. The difference came down to lubrication. Where water pooled at the base, the glacier moved smoothly. Where the base was dry, the glacier moved slowly. Friction held it in place. This meant water was not just sitting in isolated lakes. It was moving, creating a network that influenced the entire ice sheet. Mapping that network required new technology. Radar alone could not trace the full extent of the channels. So researchers combined multiple methods. They used seismic sensors to detect vibrations. When water flows through a confined space, it creates subtle tremors. These tremors travel through the ice and rock. Sensors placed across the continent could pick up those signals. They used satellite measurements to track surface elevation. When a subglacial lake fills, the ice above it rises slightly. When it drains, the ice sinks. By monitoring these tiny changes over time, scientists could watch water move through the system. They used gravity measurements to detect variations in density. Water is denser than ice. Instruments sensitive enough could map where water pooled and where it flowed. Together, these methods revealed a picture both beautiful and unsettling. Antarctica's ice sheet sat atop a constantly shifting network of water. Channels branched and merged. Lakes filled and drained in cycles. Cycles measured in years or decades. One of the most remarkable discoveries involved a river system. A system beneath the West Antarctic ice sheet. It connects inland lakes to the coast. The channel stretches for more than 1,000 kilometers. Water travels that distance slowly. The slope is gentle. The flow rate measured in meters per year, rather than meters per second. But the volume is staggering. Over time, this single system transports enormous amounts of water, enough to influence how the entire glacier behaves. When the river flows faster, the glacier slides faster. When it slows, the glacier stabilizes. The hidden hydrology controls the visible ice. This connection has profound implications. It means you cannot predict how Antarctica's ice will respond to climate change. Not without understanding what happens beneath the surface. Warm ocean water reaching the base of an ice shelf does not just melt ice from below. It accelerates the entire drainage system. More meltwater enters the subglacial rivers. The pressure increases. The glaciers lose their grip. They start sliding toward the sea. This process can happen faster than surface melting alone would suggest. The ice looks stable from above, but below, the system is already adjusting. Scientists studying these rivers describe them with a mix of fascination and concern. Fascination because the physics is elegant. Water finds its path with perfect efficiency. It responds to pressure gradients. Gradients measured in fractions of a percent. Concern because once these rivers start flowing faster, stopping them is not simple. The feedback loops are powerful. More flow creates more lubrication. More lubrication increases glacier speed. Increased speed generates more friction and heat. More heat produces more meltwater. Each step reinforces the next. The system does not gradually adjust. It shifts from one stable state to another. And those transitions can happen suddenly. In 2014, researchers observed a major drainage event. A major event in West Antarctica. A large subglacial lake that had been stable for years suddenly emptied. Over the course of months, it released billions of liters of water. Released into the river system below. The ice above the lake dropped by several meters. Instruments recorded the change in real time. Satellites watched the surface collapse. That water had to go somewhere. It flowed through the channels toward the coast. Along the way, it lubricated the base of the glacier. The glacier surged forward. The event was not catastrophic, but it was a clear demonstration. The subglacial hydrology was active, responsive, and capable of triggering large movements in the ice above. Other lakes showed similar behavior. Some filled and drained on regular cycles. Others remained stable for decades, before suddenly releasing their contents. Predicting which lakes would drain and when became a priority, because each drainage event had consequences for glacier stability, for ice shelf integrity, for sea level rise. But prediction proved difficult. The rivers are not simple pipes. They branch, they merge, they shift their paths as the ice above moves. The channels themselves are carved into both rock and ice. Over time, the flowing water melts the ice ceiling. It creates caverns. Some of these caverns are large enough to hold substantial volumes of water. When pressure builds in one part of the system, water can burst into new areas, creating sudden connections between previously isolated lakes. This dynamic behavior makes modeling extremely challenging. Every simulation has to account for variables that change faster than the models can update. Temperature, pressure, flow rate, ice thickness, geothermal heat flux. Each one influences the others. And beneath it all, the rivers keep flowing. Invisible, relentless, carving the landscape in slow motion. The people who study these systems spend months analyzing data streams, temperature readings from sensors buried in the ice, seismic traces from instruments scattered across the continent, satellite images showing minute changes in elevation. They piece together a picture of motion happening too slowly to see, but too important to ignore. Because those rivers are not just carrying water, they are carrying heat. They are transporting dissolved minerals and gases. They are connecting ecosystems that have been isolated for millions of years. And they are responding to changes in the ocean currents, changes thousands of kilometers away. Warm water creeping under the ice shelves does not stay at the coast. It mixes with the subglacial rivers. It flows inland. It raises the temperature of water that has been near freezing for ages. That temperature change has ripple effects. More melting, more lubrication, more acceleration. The rivers are becoming faster. The channels are widening. The entire system is adjusting to a new equilibrium, one that did not exist a century ago. Scientists describe this transition with careful language. They avoid alarmism, but the concern is clear in the data they share. The subglacial hydrology of Antarctica is not stable anymore. It is responding. And once these systems begin to shift, reversing them is not straightforward. The ice above may take centuries to melt, but the rivers below can change their behavior in decades, in years. That disconnect between timescales is what makes prediction so difficult. The surface looks unchanging. The depths are already moving. And in that gap between appearance and reality, the future of coastlines is being written. One flow rate at a time. One drainage event at a time. One river in the dark carrying water toward the sea. When scientists first pulled water samples from Lake Willans, they did not expect to find much. Perhaps a few hardy microbes. Perhaps nothing at all. The environment seemed too hostile. Too cold, too dark, too isolated. But the microscope revealed something different. The water was full of life. Not just alive, thriving. Thousands of distinct species. Bacteria, archaea, microorganisms that had adapted to conditions that would kill most surface life instantly. These were not dormant cells waiting for better times. They were active, metabolizing, dividing, carrying out the chemistry of life in an environment with no sunlight whatsoever. That discovery forced a rethinking of biological limits. Because these organisms were not surviving. They were functioning, building ecosystems, recycling nutrients, creating food webs entirely independent of photosynthesis. The energy sources they used came from chemistry alone. Chemosynthesis, the process of extracting energy from chemical reactions. Reactions between minerals and water. At the base of the Antarctic ice sheet, water interacts with rock. That interaction releases compounds. Iron, sulfur, methane, hydrogen. Microbes had learned to use those compounds as fuel. They oxidized iron. They reduced sulfur. They metabolized methane. Each reaction released a small amount of energy, just enough to keep cells functioning. The efficiency was remarkable. These organisms operated on energy budgets orders of magnitude smaller than surface bacteria. They divided rarely, perhaps once every few months, sometimes once a year. But they persisted, generation after generation, for millions of years. Genetic analysis revealed how isolated these populations had been. Some of the microbial DNA showed no close matches. No close matches to anything in existing databases. The lineages had diverged long ago, evolving separately in darkness. Other species had relatives in deep sea vents, or in Arctic permafrost, or in acidic hot springs. All extreme environments. All places where life had learned to endure conditions most organisms could not tolerate. But the Antarctic subglacial lakes represented something unique. Total isolation. No light penetration. No seasonal variation. No external inputs except what came from the rock below. It was a closed system. The microbes recycled everything. Carbon, nitrogen, phosphorus. Nothing was wasted. Every molecule was used and reused. The discovery raised obvious questions. How did life get there in the first place? Was it trapped when the continent froze? Or did it arrive later through cracks in the ice? The answer remains unclear. But the most likely explanation involves ancient oceans. Before Antarctica froze, it was covered by shallow seas. Those seas contained marine microbes. When the ice sheet expanded, some of those microbes became trapped in pockets of water. As the ice thickened, pressure kept that water liquid. The microbes adapted. They shifted their metabolism from light-based energy to chemical energy. Over millions of years, they evolved into the unique forms researchers find today. Separate from the surface world, following their own evolutionary path. This isolation created a natural laboratory, a place where evolution proceeded without external influence, without predators, without competition from faster-growing surface organisms. What emerged was life stripped to its essentials. No complex structures, no elaborate strategies, just the fundamental machinery of survival, operating at minimal energy. And yet, within that simplicity, there was diversity. The subglacial lakes each had slightly different chemistry, different mineral content, different temperature profiles. Those variations created distinct ecosystems. Species found in one lake were absent in another. Each body of water developed its own microbial community, shaped by local conditions. Some lakes were rich in oxygen. Others were anoxic. Some had high concentrations of sulfur. Others were dominated by iron compounds. The microbes responded accordingly. In oxygen-rich lakes, aerobic metabolism dominated. In anoxic environments, anaerobic pathways took over. But all of them shared one trait. They did not depend on sunlight. That independence made them relevant far beyond Antarctica. Because if life could exist in these conditions on Earth, then it could exist in similar conditions elsewhere. On icy moons, on frozen planets, anywhere liquid water persisted beneath a protective shell. The subglacial lakes became models for extraterrestrial oceans. Europa, Enceladus, Titan, all of them potentially held environments like this. Dark, cold, pressurized, but liquid. If microbes thrived beneath Antarctica's ice, then the odds of finding life elsewhere in the solar system increased dramatically. That connection made the research urgent. Every new discovery in the subglacial lakes added to our understanding of what life needed to survive, and what it did not need. Light was not essential. Warmth was not essential. Organic nutrients from photosynthesis were not essential. What mattered was liquid water, chemical energy, and time. Enough time for evolution to find solutions. The microbes beneath Antarctica had all three. They had been there long enough to adapt perfectly to their environment, to their limitations. They represented life at its most resilient. Not complex, not fast, but persistent. And now researchers faced a new question. What happens to these ecosystems if the ice above begins to melt? If the lakes drain? If the ancient water mixes with the modern ocean? Would the microbes survive exposure to sunlight, to oxygen levels they had never encountered, to competition from surface organisms? Or would they simply vanish, ending evolutionary lineages that had persisted for millions of years? The concern was real, because climate change was not just melting ice from above. It was altering the subglacial environment from below. Warmer ocean water reaching the base of the ice sheet was changing temperatures in the lakes, accelerating the flow of subglacial rivers, opening connections between previously isolated systems. Microbes that had evolved in one specific chemistry were suddenly encountering different conditions, different nutrients, different temperatures. Some might adapt, others might not. The ecosystems were stable because they had been isolated. Remove that isolation, and stability disappears. Scientists studying these organisms describe a strange tension. On one hand, they are eager to learn more, to sequence genomes, to understand metabolic pathways, to discover how life functions at such low energy. On the other hand, they are deeply concerned about disturbing what they are studying. Every sample taken is an intrusion. Every drill hole is a breach. The protocols for sampling are extreme. Tools are sterilized with ultraviolet light. Drilling fluids are filtered and heated. Entry points are sealed immediately after use. But even with precautions, contamination is possible. A single modern bacterium introduced into a subglacial lake could alter its chemistry, could outcompete native species, could erase millions of years of isolated evolution. That responsibility weighs heavily. The researchers know they are among the first humans to interact with these ecosystems, and possibly the last to see them in their original state. Because the ice is changing. The isolation is ending. The subglacial lakes are beginning to connect with the surface world. What happens next is uncertain. The microbes have survived isolation for longer than most species exist. But survival in isolation is different from survival in competition. The ancient water holds ancient life. And that life, however simple, represents something profound. A demonstration that biology is more flexible than we assumed. More resilient. More widespread. The subglacial ocean is not empty. It is not dead. It is quietly alive in the dark, carrying forward processes that began when Antarctica was still green. And as we learn to listen to that life, we learn something about our place in the universe. We are not the only form life takes. We are not even the most enduring. Beneath the ice, in the cold and the pressure and the endless night, existence continues. Without witness, without purpose beyond persistence. It is life for its own sake. And perhaps that is the most honest form it can take. Imagine this. An entire ecosystem that has never seen sunlight. Not for a day. Not for a year. But for 15 million years. No photosynthesis. No plants. No food chain built on light. Just chemistry. Water and rock reacting. Releasing energy molecule by molecule. And in that energy, life found a way. Not complex life. Not loud life. But persistent life. Life that divides once a year and considers that fast enough. These microbes are not waiting for conditions to improve. They are not dormant. They are living at a pace evolution designed for this exact environment. They are perfectly adapted, tuned to darkness like we are tuned to sunlight. And they have been there longer than our species has existed. That changes how you think about biology, about what is possible, about where else life might be hiding. Europa has an ocean beneath its ice. So does Enceladus. So might a dozen other worlds we have not visited yet. If microbes thrive beneath Antarctica, then those distant oceans are not empty either. They are potential homes, possible ecosystems, waiting to be discovered. The search for extraterrestrial life is not about finding something exotic anymore. It is about finding something familiar. Microbes like the ones in Lake Vostok. Simple, chemical, persistent. But here is the difficult part. Those subglacial ecosystems are fragile. Not because the organisms are weak, but because they depend on isolation. They evolved in closed systems, sealed away from competition, from predators, from the surface world. Now that isolation is ending. The ice is thinning. The lakes are draining. The ancient water is beginning to mix with the modern ocean. What happens to life that has been separate for millions of years when it suddenly encounters the present? Does it adapt? Does it vanish? Does it change the systems it enters? We do not know yet. The data is still coming in. The changes are still unfolding. But scientists watching this transition describe it with reverence. They are witnessing the end of an era, the closing of a chapter that opened long before humans walked the earth. The microbes do not know they are being studied. They do not care about climate change or melting ice. They simply continue their chemistry, extracting energy, dividing when conditions allow. But their world is changing around them, and we are part of that change, both the observers and the cause. What we do next matters. How we study these systems, how we protect them, how we decide what knowledge is worth the cost of disruption. Because once you open a sealed environment, you cannot seal it again. Once you introduce modern microbes, you cannot remove them. Once you alter the chemistry, you cannot restore it. The subglacial ocean is a gift, a window into life's possibilities. But it is also a responsibility. Let us look now at the tools we use to study it. The machines that listen to the ice. The instruments that sample water older than memory. The technology of exploration. And the limits of what it can tell us. There are places on Earth where human eyes are useless. Not because the light is dim, but because light does not reach at all. Beneath several kilometers of ice, vision offers nothing. No amount of brightness will penetrate that depth. The only way to explore is through instruments. Instruments that sense what we cannot see. Scientists call this listening. Not hearing in the literal sense, but detecting signals, vibrations, temperature changes, chemical traces, anything that reveals what lies hidden. The instruments they use are marvels of engineering, built to survive pressures that would collapse most machinery, designed to function in cold that makes steel brittle, calibrated to detect changes measured in fractions of a degree. These devices do not explore quickly. They work slowly, patiently, collecting data point by data point, building pictures of the subglacial world through indirect measurements. Radar is the foundation. It sends electromagnetic pulses into the ice. Those pulses travel downward at the speed of light. When they hit something, they bounce back. By timing how long the reflection takes, instruments can measure depth. By analyzing the strength of the signal, they can determine what the pulse hit. Ice, rock, water. Each material reflects differently. Water gives a perfect mirror-like return. Rock scatters the signal. Ice absorbs some frequencies and passes others. Over time, repeated radar scans build maps. Maps of the ice sheet's internal structure. Maps showing where lakes hide, where channels flow, where the base is wet or dry. But radar has limits. It cannot penetrate ice that is too thick. It cannot detect features smaller than a certain size. It gives shape, but not chemistry. So scientists combine it with seismic sensors. These detect vibrations. When ice cracks, it creates seismic waves. When water flows through channels, it generates low-frequency tremors. When glaciers slide over rock, they produce sustained vibrations. Arrays of seismometers placed across the continent pick up these signals. By comparing the timing between sensors, researchers can locate the source. They can tell whether the vibration came from surface movement or something deeper. This seismic listening reveals activity radar cannot detect. It shows real-time motion. Water draining from lakes. Glaciers surging. Ice shelves fracturing. The data arrives as waveforms. Lines on a screen showing amplitude and frequency. To the untrained eye, they look like noise. To someone who has studied them for years, they tell stories. A sharp spike means a crack formed. A gradual rise in frequency suggests accelerating flow. A sustained low rumble indicates a glacier is sliding faster than usual. Scientists learn to read these patterns the way others read language. Each frequency is a word. Each pattern is a sentence. But listening is not enough. To understand the chemistry of the subglacial ocean, researchers need samples. They need to touch the water itself. That requires drilling. And drilling through 4 kilometers of ice is not simple. The first attempts used mechanical drills, cutting tools that physically bore through the ice. But mechanical drills generate heat from friction. That heat can melt the surrounding ice, contaminating the very thing you are trying to reach. So engineers developed thermal drills. These use hot water to melt a path downward. Heated fluid is pumped through a narrow hose. The water melts ice on contact, creating a clean vertical shaft. The advantage is purity. Hot water drilling leaves minimal contamination. The water can be filtered before use, sterilized to remove all surface microbes. But it requires enormous energy. Melting through kilometers of ice takes days, sometimes weeks. The equipment must run constantly. Generators roar on the surface. Pumps push heated water down at precise temperatures. If the temperature drops too low, the hole refreezes. If it climbs too high, the melt accelerates too fast. Control is everything. When the drill finally approaches the subglacial lake, the team slows down. The final meters are the most critical. Penetrating the water layer must be done carefully, with instruments ready to sample immediately. Once the hole is open, they have limited time. The freezing ice wants to close the gap. Water from below wants to rush upward. Pressure equalizes. The system responds. Instruments are lowered through the hole. Some carry cameras. Some carry sensors measuring temperature and salinity. Some collect water samples in sterile containers. The descent takes hours. The instruments pass through layers of ice with different properties. Each layer represents a different era. Compressed snow from centuries past. When the instruments reach liquid water, the readings change immediately. Temperature rises slightly. Pressure equalizes. The sensors detect movement. Currents flowing in the darkness. Cameras capture the first images of the lake bottom. Sediment lies undisturbed. In some areas, microbial mats coat the rock. Thin films of biological activity. Barely visible, but undeniably present. Samples are collected and sealed. Then the instruments are pulled back to the surface. The entire process monitored. to ensure nothing from above falls into the lake. What comes up through those holes is more than water. It is information, chemical composition, isotopic ratios, microbial DNA, temperature profiles, each droplet analyzed in detail, each microbe sequenced, each molecule identified. The laboratories that process these samples are as sterile as operating rooms. Scientists work in sealed environments. They wear protective gear. Every surface is cleaned repeatedly, because contamination works both ways. Surface microbes cannot enter the lake, but ancient microbes brought to the surface must not escape either. No one knows how those organisms would behave in open air, whether they would survive, whether they could adapt to oxygen levels they have never experienced. The caution is necessary, not from fear, but from respect, for the systems being studied, for the knowledge being gained, and for the possibility that what lies beneath Antarctica could change our understanding of life itself. The instruments keep listening, season after season. Data streams flow from sensors buried in the ice. Seismic stations record vibrations day and night. Satellites measure surface changes from orbit. Together, these tools create a portrait of motion. The ice is not still. The lakes are not static. The rivers flow in darkness. And beneath it all, the ocean breathes. Slowly, patiently, waiting for the next measurement, the next discovery, the next question that the data cannot yet answer. The technology of exploration has limits. It can detect but not see. It can measure but not predict. It can sample but not understand completely. Yet with each improvement, the picture becomes clearer. The subglacial world emerges from shadow into outline, from mystery into mechanics. The ice speaks through instruments, and the instruments translate that speech into numbers, into graphs, into models that try to capture complexity in equations. It is an imperfect translation, but it is the only one we have, and it is enough to reveal something profound. That beneath the frozen surface, the planet continues its work, shaping, flowing, living, unaware of the machines that listen to its rhythm. The instruments will keep recording, collecting data that future researchers will analyze, building archives that might outlast the ice itself. Because the ice is changing, but the measurements remain, frozen in digital memory, preserved for when understanding finally catches up to observation. Antarctica feels distant, a white expanse at the bottom of maps, separate from the daily concerns of cities and coasts. But distance is an illusion. The ice sheet is connected to everything, through ocean currents, through atmospheric patterns, through the physics of water and heat. What happens beneath Antarctica's ice affects weather systems thousands of kilometers away. It influences sea levels. It shapes marine ecosystems. It regulates the planet's temperature. That connection is not obvious. You cannot see it, but the data reveals it clearly. The subglacial ocean is part of a global system. When it changes, the effects ripple outward, sometimes slowly, sometimes with surprising speed. Understanding that connection requires looking at the ocean surrounding Antarctica. The Southern Ocean, the coldest ocean on Earth. This ocean is not like others. Its water is dense, heavy with salt and cold. That density makes it sink, deep below the surface. As it sinks, it forms currents. Cold water flows northward along the ocean floor, traveling beneath warmer surface layers, circulating through every ocean basin. This deep circulation is called the thermohaline current. It moves slowly. A single water molecule might take 1,000 years to complete the loop. But the volume is immense. The current carries oxygen to the deep ocean. It distributes nutrients. It regulates global temperature by moving heat from the equator toward the poles. Antarctica drives this system. The formation of dense water near the ice shelves keeps the current flowing. Remove that process, and the entire circulation weakens. Now consider what happens when ice shelves thin. When warm water reaches their base. When melting accelerates. The meltwater entering the ocean is fresh, not salty. It is lighter than seawater. It floats on the surface instead of sinking. This changes the density structure. Less dense water means less sinking. Less sinking means weaker circulation. Weaker circulation means slower heat distribution. The effects cascade. Ocean currents shift. Weather patterns adjust. Ecosystems respond to changes in temperature and nutrient availability. Scientists studying these connections describe them as feedbacks. Each change triggers another change. The system is interconnected. Melting ice alters ocean salinity. Altered salinity affects currents. Changed currents modify climate patterns. Modified climate accelerates melting. The cycle reinforces itself. And once it begins, slowing it is difficult. But the connection runs deeper than surface currents. The subglacial ocean itself is changing, responding to warmth from below and pressure from above. Warm ocean water does not stay at the coast. It flows under the ice shelves, finding channels carved into the rock, following path of least resistance. As it moves inland, it encounters the base of the ice sheet, where ice meets water, where the grounding line sits. The grounding line is critical. It is the point where ice transitions from resting on rock to floating on water. Inland from this line, the glacier is grounded. Beyond it, the ice shelf floats. That transition zone determines stability. If warm water melts ice near the grounding line, the ice shelf loses support. It begins to float sooner. The grounded portion retreats. When grounded ice becomes floating ice, it moves faster. Without friction against the bedrock, it slides toward the sea, thinning, fracturing, eventually breaking apart. This process is already underway. Satellites measure the position of grounding lines across Antarctica. Many are retreating, some faster than models predicted. The retreat is not uniform. Some glaciers remain stable. Others accelerate dramatically. The difference comes down to local conditions. Bedrock shape, ocean temperature, ice thickness. But the trend is clear. The grounding lines are moving backward. The ice is losing its grip. And the subglacial hydrology is responding. More warm water means more basal melting. More melting creates more meltwater. More meltwater lubricates the glaciers. lubricated glaciers slide faster. The subglacial rivers swell. Lakes fill and drain more frequently. The entire drainage system accelerates. This is not speculation. Instruments measure it in real time. Flow rates increase. Pressure changes occur more often. The ice responds within months to changes in ocean temperature. That rapid response surprised many researchers. They expected the system to change slowly, over centuries. Instead, it adjusts within years. The implications are stark. Sea level rise projections based on slow ice sheet response are too conservative. The ice can move faster than those models assumed. Not catastrophically fast, but faster than comfortable. Enough to affect coastal planning. Enough to require adaptation sooner than expected. The numbers are still uncertain. Models struggle with complexity. Too many variables interact in ways that are difficult to simulate. But the direction is clear. The Antarctic ice sheet is contributing to sea level rise. That contribution is increasing. And the subglacial ocean is part of the mechanism. Researchers studying this connection work with a sense of urgency. Urgency tempered by realism. They know the changes are underway. They know the physics is irreversible on human timescales. But they also know that understanding the details matters. Predicting where ice will melt fastest helps prioritize where to study. Knowing which glaciers are most vulnerable guides which instruments to deploy. The research is not just academic. It has practical consequences. For cities built at sea level. For infrastructure designed with old assumptions about coastlines. For populations that will need to adapt. Antarctica's subglacial ocean is not separate from those concerns. It is central to them. Because the water flowing beneath the ice today will reach the surface eventually. And when it does, it will raise the ocean everywhere. The connection is physical, undeniable, measured in data that accumulates year after year. The ice sheet holds enough water, enough to raise global sea levels by nearly 60 meters if it melted completely. No one expects that to happen soon, but even partial melting is significant. A meter of sea level rise displaces millions of people. 2 meters reshapes coastlines. 5 meters rewrites maps. The subglacial ocean is part of the system determining how fast that happens. The rivers flowing in darkness are carrying Antarctica's future toward the sea. Drop by drop, year by year. And the instruments keep measuring. Recording flow rates, monitoring temperatures, tracking the movement of water. Water that most people will never see, but everyone will eventually feel. The climate connection is not abstract. It is immediate, present, unfolding in real time beneath ice that looks unchanged from above. That is the challenge. The surface appears stable, but the depths are already shifting. And by the time the surface shows the change, the momentum will be too great to stop. The ice sheet is not fragile. It is resilient. It has survived warmer periods before. But resilience has limits. And those limits are being tested now. Tested in ways they have not been tested in millions of years. Antarctica's subglacial ocean is waking up. The question is not whether it will change. It is how fast, and how much of that change we can prepare for before it arrives. Here is something to consider. Every coastline on Earth is connected to what happens beneath Antarctica's ice. Not through politics, not through economics, but through physics, through water, through the simple fact that ocean levels rise when ice melts. The subglacial ocean contains enough water to reshape continents. Not all at once, but over time. Enough time to matter to cities, to infrastructure, to populations living near the sea. Right now, that water is flowing, moving through channels under the ice, finding paths toward the ocean, responding to warmth that should not be there. The glaciers are sliding faster. The ice shelves are thinning. The grounding lines are retreating. All of this is measured, documented, undeniable. But it is happening slowly. Too slowly to make headlines. Too slowly to feel urgent. Yet fast enough that within a human lifetime, the consequences will be visible. Sea level rise is not a future problem anymore. It is a present one. Already happening. Already measurable. Already affecting planning decisions for coastal cities. And Antarctica is driving a significant portion of that rise. Not the only contributor, but a major one, and one that is accelerating. The challenge is time. The ice sheet responds slowly to change. But once it starts moving, it continues for centuries. Even if temperatures stabilize tomorrow, the momentum is already built in. That is the difficult truth. The subglacial rivers will keep flowing. The lakes will keep draining. The ice will keep sliding toward the sea. Not because the planet is angry. Not because nature is punishing us. But because physics does not care about intention. Only about energy. Heat, pressure, flow. The water beneath Antarctica is older than our species. It remembers climates we have never seen. It contains chemistry that evolved in isolation for millions of years. But now it is reconnecting with the modern world, mixing with currents that circle the globe, entering systems that regulate temperature and weather across continents. What happens next depends partly on what we do, how fast we change, how much we adapt, how seriously we take measurements. Measurements that describe processes too slow to witness directly. But it also depends on forces beyond our control. The momentum already present in the system. The feedbacks already triggered. The thresholds already crossed. Antarctica's ice will keep changing. The question is only the rate, and whether we can live with the consequences of changes we set in motion decades ago. The subglacial ocean is patient. It has endured for millions of years. It will persist in some form long after we are gone. But its current state is not permanent. Nothing about this system is permanent. It flows. It adjusts. It responds. And we are part of what it is responding to, whether we acknowledge it or not. Let us turn now to the parallels, to the other worlds where similar oceans might exist, to the search for life that uses Antarctica as its model. Because if we are asking questions about the ice beneath our feet, we must also ask about the ice covering distant moons. When spacecraft first imaged Europa, scientists saw something familiar. Cracks, ridges, patterns in the ice that looked like pressure fractures. The surface was bright, reflective, young in geological terms. Something was resurfacing it, smoothing out craters, erasing old features. The explanation became obvious once they studied the data. Beneath Europa's frozen shell was an ocean. Liquid water, kept warm by tidal forces from Jupiter's gravity. That ocean was not small. It likely contained more water than all of Earth's oceans combined. Trapped beneath ice, perhaps 20 kilometers thick. The parallels to Antarctica were immediate. Both had ice shells covering liquid water. Both had environments sealed from sunlight. Both created conditions where chemosynthesis could replace photosynthesis. If life existed beneath Antarctica's ice, then life could exist beneath Europa's ice. The same physics, the same chemistry, the same possibilities. That connection changed the search for extraterrestrial life. It shifted focus from planets to moons, from surfaces to subsurfaces, from heat to hidden oceans. Saturn's moon, Enceladus, reinforced the pattern. The Cassini spacecraft flew through plumes of water vapor, plumes erupting from its south pole. Analysis showed the plumes contained salt, organic molecules, traces of hydrogen, all the ingredients for life as we understand it, all coming from an ocean beneath the ice. Enceladus became another model, another comparison to Earth's own buried seas. The discoveries in Antarctica's subglacial lakes provided context. Context for these alien oceans. They showed what to look for, what signatures might indicate life, what chemistry could sustain ecosystems without light. Every microbe found beneath the Antarctic ice sheet made life on icy moons more plausible. Every metabolic pathway discovered added to the list of strategies life might use elsewhere. The research became bidirectional. Scientists studying Antarctica's subglacial ecosystems were also studying potential analogues for Europa. Engineers designing drills for Lake Vostok were designing prototypes. Prototypes for eventual missions to icy moons. The techniques were the same: sterilization, contamination prevention, minimally invasive sampling, all necessary whether drilling through Earth's ice or landing on Europa's surface. But the parallels went beyond method. They revealed something fundamental about planetary physics. Icy worlds were not rare. They were common. Almost every large moon in the outer solar system showed signs of subsurface water. Europa, Enceladus, Ganymede, Titan, possibly Triton. Each one a potential ocean. Each one a possible home for life. All hidden beneath frozen shells. The pattern suggested that oceans were not special to Earth. They were a natural outcome of planetary formation. Given the right size and orbit, moons developed liquid interiors, kept warm by tidal heating or residual formation energy. Antarctica's subglacial ocean became proof of concept. It demonstrated that life did not need the surface. It could thrive in darkness if water and chemistry allowed. That shifted expectations. The search for life was not about finding Earth-like planets anymore. It was about finding liquid water. Anywhere. Under any conditions. And the most likely places to find that water were beneath ice. Sealed away. Protected. Persistent. The scientists who studied Antarctic lakes began collaborating with planetary scientists. Microbiologists who sequenced subglacial microbes worked with astrobiologists. Astrobiologists modeling Europa's chemistry. The boundary between Earth science and space science blurred. Because the questions were the same. How does life survive in darkness? What energy sources does it use? How isolated can an ecosystem be and still function? Antarctica provided answers. Partial answers, but enough to guide the search elsewhere. When future missions finally drill through Europa's ice, the techniques will have been tested beneath Antarctica. The instruments will be refined versions of those used in Lake Vostok. The protocols will be adapted from years of subglacial exploration on Earth. But the parallels also carried warnings. If drilling could contaminate Antarctic lakes, it could contaminate Europa. If surface microbes could alter ancient ecosystems on Earth, they could do the same on other worlds. The ethics of exploration became more complex, because the ice was not just a scientific target anymore. It was a potential biosphere, one that might have been functioning for billions of years. Disturbing it required justification, understanding the consequences, accepting responsibility for what might be introduced or destroyed. Antarctica taught those lessons. Each contamination scare, each protocol revision, each discovery of unexpected sensitivity in subglacial ecosystems. The experience informed how future missions should be designed. Not to conquer, but to observe, to sample carefully, to learn without erasing. The mirror works both ways. Studying Antarctic ice helps us understand Europa. But studying Europa helps us understand Antarctica. The same physical processes operate on both worlds. Ice fractures under pressure. Water flows through channels. Chemistry happens where liquid meets rock. These are universal, not unique to Earth. Recognizing that universality changes perspective. Earth is not special. It is one example of common processes. A laboratory where we can study phenomena that occur throughout the solar system. The subglacial ocean beneath Antarctica becomes a window, not just into Earth's past, but into the present state of distant worlds, into the possibilities of life wherever water persists. That realization is both humbling and inspiring. Humbling because it shows how little is unique about our world. Inspiring because it suggests life might be everywhere that conditions allow. The frozen moons are not dead. They are sealed, protecting what lies within. Just as Antarctica's ice protects the lakes beneath. And if those moons hold life, it will likely resemble what exists in Antarctic darkness. Simple, chemical, persistent. Life that does not depend on sunlight or warmth, only on water and time. The search continues. Missions are being designed. Instruments are being built, all informed by what we have learned beneath Earth's ice. When those missions launch, they will carry knowledge. Knowledge gained from years of Antarctic research. From drilling through kilometers of frozen time. From sampling water older than civilization. From discovering life where it should not exist. The mirror of other worlds reflects back at us, showing that the questions we ask about Antarctica are the same questions we must ask about everywhere else. Where is the water? What keeps it liquid? What lives in the darkness? And what do we risk by looking? The answers are not complete. They may never be complete. But each discovery adds a piece. Each Antarctic lake reveals something applicable beyond Earth. And each time we lower an instrument through the ice, we are practicing. Practicing for a greater exploration. One that will eventually reach beyond this planet. Into the frozen moons. Into the hidden oceans. Into the places where life might be waiting. Silent, patient, unchanged for eons. Just like the microbes beneath Antarctic ice. The mirror shows us ourselves, reflected in alien environments, connected by physics, by chemistry, by the simple fact that water is water. Wherever it flows, something is changing. The data shows it clearly. The ice is moving faster. Not everywhere, but in critical locations. Glaciers that have been stable for centuries are beginning to slide. Ice shelves that looked permanent are thinning. The subglacial rivers are flowing with more volume, more speed. This is not speculation. It is measurement. Satellites track surface velocity. Seismic sensors record basal motion. Instruments buried in the ice measure temperature and pressure changes. The numbers tell a consistent story. The Antarctic ice sheet is accelerating its slide toward the sea. In West Antarctica, the acceleration is most pronounced. The glaciers there rest on bedrock below sea level. That geometry makes them vulnerable. Once warm water reaches their base, retreat becomes difficult to stop. The Thwaites Glacier has become a focal point. It is enormous, wide enough to cover an area larger than Great Britain, thick enough to hold substantial volume. And it is retreating. The grounding line has moved inland by several kilometers. Moved in recent decades. The ice shelf protecting its front is fracturing. Large cracks run through it, growing longer each year. If Thwaites collapses entirely, it would raise sea levels by more than 1/2 meter. But the concern goes beyond that single glacier. Thwaites acts as a plug. It holds back ice from the interior. If it fails, the glaciers behind it could accelerate, creating a chain reaction. One collapse leading to another. Scientists studying the region describe it with measured language. They avoid alarmism. But the concern is evident. The system is more unstable than previous models suggested. Warm ocean currents are reaching the grounding line, melting ice from below. The subglacial hydrology is responding. Lakes are draining faster. Rivers are carrying more water. The acceleration feeds itself. More melting creates more lubrication. More lubrication increases speed. Increased speed generates more friction. More friction produces more heat. More heat accelerates melting. Each step reinforces the next. The system does not stabilize easily once this cycle begins. Other regions show similar patterns. The Pine Island Glacier, the Totten Glacier, multiple sites where acceleration is documented, where retreat is ongoing. The ice sheet is not collapsing. Not yet. But it is changing faster than expected. Faster than comfortable. Models built on historical data struggle to match current observations. The real world is outpacing the simulations. That gap between prediction and reality is what concerns researchers most. Because if the models are wrong about the rate of change, they might be wrong about the timing too. About when critical thresholds will be crossed. About how much time remains before irreversible processes take over. The term used is tipping point, a moment when the system shifts from one stable state to another, when feedback loops become self-sustaining. Antarctica may be approaching such points, or may have already passed some of them. The uncertainty is part of the problem. The data is incomplete. The processes are complex. But what is clear is that the acceleration is real, measurable, ongoing. The subglacial ocean is part of this acceleration. Its hidden rivers carry water toward the coast. Its lakes drain more frequently. Its chemistry responds to temperatures that are climbing. Climbing, however, slowly. This is not just about ice physics anymore. It is about the interaction between ice and water, between frozen and liquid, between stable and dynamic. The boundary between those states is blurring. Ice that should be solid is behaving more like fluid, flowing, deforming, responding to forces it once resisted. Researchers describe watching this transition in real time. They see glaciers that moved centimeters per year, now moving meters per year. They see ice shelves that were thick becoming fragile. They see systems that were predictable becoming chaotic. The acceleration is not uniform. Some regions remain stable. Some even thicken as snow accumulation increases. But the overall trend is clear. More ice is leaving Antarctica than accumulating on it. That imbalance shows up in global sea level measurements. Satellites detect the rise. Tide gauges confirm it. The ocean is gaining water. Antarctica is one of the sources. The rate of contribution is increasing. Not dramatically, but steadily. Each year slightly more than the last. Projections for sea level rise keep being revised upward. What seemed like a problem for the 22nd century now looks like a challenge for this century. What seemed gradual now appears accelerating. The people living on coasts will feel this change. Not tomorrow, but within decades. Rising water during storms. Flooding that occurs more frequently. Infrastructure that needs adaptation. The subglacial ocean beneath Antarctica is connected to those consequences. Its hidden motion contributes to visible change. Its ancient water is becoming modern water, joining circulation systems that affect everywhere. Scientists studying this acceleration work with a sense of urgency. Not panic, but focus. They know that understanding the details matters for preparing, for adapting, for making decisions about the future. They deploy more instruments. They refine models. They collect data that might reveal patterns, might predict which glaciers will fail next, might give warning before critical changes occur. But they also acknowledge limits. Some processes are too complex to model precisely. Some feedbacks are too sensitive to initial conditions. Some changes are already locked in, already irreversible on human timescales. The acceleration will continue. The ice will keep sliding. The subglacial rivers will keep flowing. Because physics does not pause. It only responds to energy, to heat, to pressure, and the energy in the system is increasing. From warming air, from warming oceans, from changes that began decades ago and will continue for decades to come. The ice sheet is not fragile, but it is finite. It has limits, and those limits are being tested. Tested in ways they have not been tested in millions of years. Antarctica's response is slow by human standards, but fast by geological ones. What takes centuries for ice takes only moments in planetary time. The acceleration we measure today is just the beginning, a preview of changes that will unfold over generations, that will reshape coastlines, that will require adaptation on scales rarely attempted. The subglacial ocean is waking up, its ancient stillness giving way to modern motion, its sealed chemistry opening to external forces, its isolated ecosystems beginning to connect. What that means for the future is still unfolding, still being discovered, still being measured by instruments. Instruments that listen to the ice as it accelerates toward change. There is a moment in every long story when movement becomes inevitable, when forces align, when resistance weakens, when the system tips. Antarctica is in that moment now, not at the beginning of change, not at the end, but in the acceleration, the phase where everything happens faster than before. Glaciers that held for centuries are sliding. Ice shelves that looked permanent are fracturing. The subglacial rivers that flowed slowly are racing faster. This is measured, documented, undeniable. The data comes from satellites, from sensors buried in the ice, from instruments that record motion invisible to the eye. The acceleration is not catastrophic, not yet, but it is consistent. Each year slightly faster than the last. Each measurement slightly higher than expected. What does this mean? It means the ice sheet is responding to warmth, to pressure, to changes that began before most of us were born. It means the balance that held for millions of years is shifting, tipping toward a new state, one where ice moves faster, where sea levels rise more quickly, where coastlines need adaptation. This is not distant future. This is present, happening right now beneath ice that looks unchanged from space. The challenge is visibility. The surface appears stable, but the depths are already moving. By the time the surface shows the change, the momentum will be unstoppable. That is the nature of ice sheets. They respond slowly, but once they start, they continue. For decades, for centuries, long past the point where the forcing stops. We are witnessing the beginning of that response, the early phase of acceleration, the moment when gradual becomes rapid, when theoretical becomes real. The subglacial ocean is part of this story. Its hidden water is lubricating the base. Its ancient chemistry is entering modern systems. Its flow is accelerating the ice above it. Every measurement adds to the picture. Every data point confirms the trend. Every model update revises the timeline shorter. The ice is moving. The question is not whether it will continue, but how fast, and whether we can adapt to the changes it brings. Because adaptation is possible. Planning helps. Understanding the processes buys time. Predicting which glaciers fail first allows preparation. But adaptation requires acknowledgement, recognition that the acceleration is real, that the consequences are coming, that the time to respond is now. The subglacial ocean beneath Antarctica is waking up. And when it wakes fully, the world will feel it. From the coastlines to the climate, from the currents to the weather patterns. This is not about fear. It is about physics, about responding to measurements that tell an uncomfortable truth. The planet is changing, and we are part of that change. Let us look now at what the future holds, at the projections, at the scenarios, at what happens when the acceleration continues. Despite decades of research, Antarctica's subglacial ocean remains mysterious. Every answer creates new questions. Every measurement reveals more complexity. Scientists have mapped the major lakes. They have traced the largest rivers. They have sampled water and found life. But vast regions remain unexplored, unknown. There are parts of East Antarctica where ice is so thick that radar cannot penetrate fully, where the base remains a blur, where lakes might exist but cannot be confirmed. There are channels that appear on satellite images, but whose connections remain unclear. Water moves through them, but where it starts and where it ends is speculation. There are chemical signatures in the samples, signatures that do not match known processes, isotope ratios that suggest reactions no one has observed, molecules that hint at pathways not yet understood. The subglacial ecosystem is more complex than initial discoveries suggested. Different lakes host different communities. The connections between them shape which species spread, and which remain isolated. But how those connections work over long time scales is unknown. Whether microbes travel through the subglacial rivers, whether isolation creates new species, or whether mixing prevents differentiation. The role of geothermal heat is still debated. Some models suggest volcanic activity beneath the ice, hotspots that keep certain regions warmer. But direct measurements are difficult. The ice is too thick, the locations too remote. If geothermal sources exist, they could create local ecosystems. Ecosystems different from the rest. Warmer water, different chemistry, possibly more complex life. But proving this requires drilling in areas no one has reached, deploying instruments where logistics are nearly impossible. The questions remain open. Another unsolved mystery involves the age of the subglacial water. Some of it is clearly ancient, sealed for millions of years. But other samples show younger signatures, as if connected to surface melt from recent periods. How can both be true? How does water that young reach lakes that old? The answer likely involves complex mixing, pathways that occasionally open, events that temporarily connect isolated systems. But the details are unclear. The mixing patterns are not mapped. The timescales are uncertain. Scientists also puzzle over the chemistry of the sediments. The layers at the bottom of the lakes contain organic material, some of it clearly biological. But some samples show structures that are ambiguous. Are they fossils? Are they mineral formations? Are they something in between? Without more samples, the questions cannot be resolved. And sampling is not easy. Each drill site costs millions, takes years to complete, risks contamination. The number of sites that can be studied is limited. So choices must be made. Which lakes to target? Which questions to prioritize? Which mysteries to pursue with finite resources? The subglacial ocean is vast. The Antarctic ice sheet covers 14 million square kilometers. Much of it hides water. Most of it has never been sampled. What we know comes from a handful of sites, a few dozen measurements across an entire continent. The picture is incomplete by necessity. Another major question involves prediction. How fast will the subglacial hydrology change as climate warms? Will the acceleration continue? Will it stabilize? Will it trigger collapse? The models disagree. Different assumptions produce different outcomes. Some show gradual change. Others show rapid transitions. The uncertainty is large. Part of the difficulty is data. The observations are too recent. The baseline too short. Ice sheets change over centuries. We have decades of measurements. Extrapolating from short records to long timescales is risky. Small errors compound. Unexpected processes emerge. The subglacial rivers might behave differently under warmer conditions. New channels might open. Old ones might close. The entire drainage pattern could reorganize. But predicting that reorganization is beyond current capability. The system is too complex. The variables too interconnected. Scientists studying these questions often express frustration. Not with the difficulty, but with the stakes. The answers matter. For coastlines, for climate, for life. Yet the answers remain elusive, hidden beneath ice that will not give up its secrets easily. There are also questions about time. How long has the subglacial ocean existed? Did it form when Antarctica froze? Or did it exist before, persisting through multiple climate cycles? The isotope data suggests long isolation. But isolation can occur in different ways. Sealed continuously, or sealed intermittently with rare connections. Distinguishing between these scenarios requires evidence that is difficult to obtain. Core samples from deep sediments, ice cores that reach the base, chemical analyses of extreme precision. Each piece of evidence adds constraints, but the full picture remains out of reach. The timeline of the subglacial ocean is still being written. And what about the future? If the ice sheet collapses partially, if the subglacial lakes drain, what happens to the ecosystems that have survived for millions of years? Do they adapt? Do they perish? Do they spread into the modern ocean and thrive? Or do they vanish as soon as they encounter sunlight and competition? The microbial communities beneath the ice are unique. They represent evolutionary lineages that diverged long ago. Losing them would be losing part of Earth's biological heritage. But protecting them might not be possible. If the ice melts, the isolation ends. No amount of caution can preserve what climate change will expose. That tension between study and preservation defines much of the research. Scientists want to learn, but they also want to protect. The balance is difficult. Some argue for minimal intervention. Study only what is necessary. Leave the rest undisturbed. Let the subglacial ocean remain as unknown as possible. Others argue the opposite. Study intensively while the isolation still exists. Document everything before it changes. Collect samples before they are lost. Both perspectives have merit. Both come from concern rather than indifference. The questions are ethical as much as scientific. What we do not know about Antarctica's subglacial ocean far exceeds what we do know. The mapped lakes are a fraction of what likely exists. The sampled water represents a tiny percentage of the total volume. The microbial diversity is certainly higher than current catalogues suggest. The chemistry more varied. The connections more complex. Every expedition reveals surprises. Every analysis finds unexpected results. The system refuses to fit into simple categories. That resistance to simplification is part of what makes it compelling. The subglacial ocean does not behave like surface systems. It operates by different rules. Rules we are still learning. The unsolved questions are not failures of science. They are reminders of scale, of complexity, of how much remains beyond current understanding. Antarctica's hidden water is patient. It does not care whether we understand it. It simply continues, flowing, existing, shaping the continent in darkness. The questions will persist. New ones will emerge. Some might be answered. Others might remain open for generations. But the pursuit matters, because in trying to understand the subglacial ocean, we learn about more than ice and water. We learn about limits, about interconnection, about the planet's capacity to surprise us. The unsolved questions keep researchers returning, season after season, drilling deeper, measuring more precisely, building better models, not because they expect complete answers, but because partial answers are valuable. Each piece of the puzzle reveals something about Antarctica, about Earth, about life's possibilities. The subglacial ocean remains unsolved. That is both frustrating and appropriate. Some mysteries are not meant to be resolved quickly. They require patience that matches their timescale. Millions of years to form. Decades to begin understanding. Perhaps centuries to fully comprehend. If comprehension is even possible. For now, the questions outnumber the answers. The unknowns exceed the knowns. And the ice keeps its secrets close. There is a particular kind of quiet that exists only in extreme places. Not the quiet of empty rooms, but the quiet of vast distance, of isolation so complete that sound itself seems unnecessary. Antarctica possesses this quiet, especially in winter, when the continent is sealed by darkness and cold, when the wind dies and the ice settles, when everything human stops and only the planetary rhythms continue. Researchers who spend extended time there describe the weight of that silence, how it presses against perception, how it makes you aware of your own internal noise. The blood moving, the breath cycling, the thoughts that will not stop. Against that backdrop, the idea of the subglacial ocean takes on different meaning. Not as data, not as measurements, but as presence. Something vast and hidden moving beneath the silence. You cannot hear it, but knowing it exists changes the experience of standing on the ice. The ground beneath your feet is not ground. It is a ceiling, separating you from a liquid darkness, a darkness that stretches for hundreds of kilometers. That awareness creates a strange duality. The surface world of light and cold, the deep world of pressure and flow, both occupying the same space, separated by ice that seems solid but is actually in constant motion. The weight of that separation is psychological. It reminds you that the familiar is temporary, that what looks permanent is changing, that beneath every certainty lies something deeper, more fundamental, less knowable. Scientists are not immune to these feelings. They work with numbers and instruments, but they also stand in the cold. They watch the horizon. They feel the scale of what they are studying. Some describe it as humbling, others as unsettling. A few find it peaceful. The recognition that the planet operates at scales that make human concerns seem small. The silence of Antarctica is not empty. It is full of motion too slow to hear, too deep to sense, but present nonetheless. The ice creaks occasionally, a sharp crack that echoes across the plateau, then returns to quiet. Those cracks are the sound of the ice sheet adjusting, releasing stress, responding to forces from below. Each crack represents movement, microscopic shifts accumulating over years. The ice does not move suddenly. It moves continuously, and that continuous motion creates pressure that must occasionally be released. The subglacial ocean contributes to those pressures. When lakes fill, the ice above rises. When they drain, it sinks. The surface responds to the depth with a lag. The signal takes time to travel upward. Standing on that surface, you are standing on a system in constant communication with itself. Ice and water exchanging information through pressure, through temperature, through the physics that connects all parts of the continent. The weight of silence becomes the weight of time, because the ice records history in its layers. Every year adds a thin band of snow, compressed by the weight above, transformed into ice that holds bubbles of ancient air. Those bubbles are messages from atmospheres long past, from climates that no longer exist, from moments in Earth's history captured and frozen. When researchers drill through the ice and release those bubbles, they are breaking a seal that has lasted millennia. The air that escapes is older than civilization, older than agriculture, older than any human memory. That air has been silent all that time, trapped, waiting, now released into the modern atmosphere where it becomes indistinguishable from everything else. The same is true for the subglacial water. It has been silent beneath the ice for millions of years, moving slowly, existing without witness, its chemistry unchanged except by the slowest geological processes. When samples are brought to the surface, that silence is broken. The water is exposed to light, to oxygen, to temperatures it has not experienced since before the ice formed. What happens to it then is unknown. Whether it remains stable, whether the microbes within survive or die, whether the chemistry shifts immediately or holds its ancient balance. The weight of silence is also the weight of responsibility. Because once you break that seal, you cannot restore it. Once you introduce contamination, you cannot remove it. Once you alter a system that's old, the change is permanent. Researchers carry that weight. They design protocols to minimize impact. They sterilize equipment. They work slowly, but they know perfection is impossible. Every sample collected is an intrusion. Every measurement a disturbance. The very act of observation changes what is being observed. That paradox defines the work. To understand, you must touch. But to touch is to alter. The balance between knowledge and preservation is never perfect. In the Antarctic silence, those tensions become clear. There is no noise to hide behind. No distraction from the ethical questions. Just the eyes, the instruments, and the awareness of what lies beneath. Some researchers speak of feeling watched, not by consciousness, but by time itself, by the accumulated history of the continent, by the systems that have functioned without human input for longer than humans have existed. It is an irrational feeling, but persistent. The silence makes you aware that you are the anomaly, not the ice, not the water, not the microbes in the darkness. You are the temporary visitor, the brief disturbance, the passing phenomenon that will leave no lasting trace, except in the data you collect. The ice will remain. The subglacial ocean will continue, long after the research stations are abandoned, long after the last instrument fails, long after the last sample is analyzed. That continuity is part of what makes Antarctica compelling. It reminds you that the planet's processes are independent. They do not require observation. They simply are. The weight of silence is the weight of that independence. The recognition that your presence does not matter to the ice. Your questions do not change its behavior. Your concerns do not alter its physics. It responds only to energy, to pressure, to heat, the forces that have shaped it for millions of years, and will continue shaping it for millions more. Standing in that silence, you become aware of your own temporariness. The human tendency to think in decades feels inadequate. Measuring change requires thinking in centuries. Understanding the system requires thinking in millennia. The subglacial ocean operates on those timescales. Its circulation measured in thousands of years. Its chemistry balanced over millions. Its life adapted to rhythms that make human generations seem like moments. In the weight of Antarctic silence, those scales become tangible. Not abstract, not theoretical, but felt through the cold that never truly warms, through the horizon that never truly changes, through the ice that moves too slowly to see but never stops moving. The silence is not peaceful. It is patient, waiting for the noise of humanity to pass, waiting for the instruments to fail, waiting for the questions to be forgotten. Because beneath it all, the water keeps flowing. The ice keeps breathing. The continent keeps its slow conversation with time. And in that conversation, human voices are barely whispers. Brief sounds that fade quickly into the immensity of geological patience. The weight of silence is the weight of recognizing that, of standing on the ice and understanding that you are infinitesimal, that your understanding is partial, that your impact, however careful, is still impact. And yet the work continues, because partial understanding is better than ignorance, because careful impact is better than reckless. Because the silence, however heavy, invites questions that matter. Questions about life, about time, about what persists when everything else changes, about what it means to study something you can barely reach and cannot fully comprehend. The silence offers no answers. It only deepens the questions, makes them heavier, more substantial, more impossible to ignore. Beneath Antarctica's ice, the ocean moves in that silence, patient as stone, older than memory, waiting for nothing because it needs nothing, simply existing in the dark. And those who study it carry the weight of that existence, the knowledge that what they touch is beyond full understanding, that what they measure is larger than measurement, that what they disturb has no concept of disturbance. The silence holds all of that. The questions, the uncertainty, the vast patient presence of water in darkness, moving slowly toward a future no one can predict. Silence has weight, not physical weight, but presence, the kind that settles in your chest. When you stand in places where human noise fades to nothing. Antarctica has that silence. Deep, complete, undisturbed by anything except the planet's own rhythms. Standing there, you become aware of what lies beneath. Not through sound, but through knowledge. The awareness that under several kilometers of ice, water is moving. Has been moving. For longer than language has existed. That awareness changes perception. The ground is not solid. It is a barrier between the world of light and the world of liquid darkness. The silence above mirrors the silence below. Both absolute, both patient, both indifferent to human timescales. This is not about fear. It is about scale, about recognizing that the systems we study operate independently. They do not need our attention. They do not change because we observe them. They simply continue, flowing, existing, shaping themselves according to physics that predates all observation. The weight of that realization is what many researchers describe. Not burden, but presence, the feeling of standing at the edge of something far larger than comprehension. The subglacial ocean is not unknowable because it is complex. It is unknowable because it operates at scales we cannot fully inhabit. Our measurements are snapshots, moments in processes that span geological time. Every data point is accurate, but accuracy is not completeness. We see fragments, pieces, reflections of a whole that remains just beyond reach. And perhaps that is appropriate. Perhaps some systems are meant to remain partially mysterious, not from lack of trying, but from recognition that full understanding might not be possible. The silence teaches that. It reminds you that limits exist, not in technology, not in method, but in the fundamental gap between human timescales and planetary ones. We live in decades. The ice lives in millennia. We measure in years. The subglacial ocean circulates over thousands. The gap is unbridgeable except through imagination. But imagination informed by measurement is powerful. It allows us to picture what we cannot see, to sense what we cannot touch, to understand, however partially, what exists in the darkness. The weight of silence is also the weight of responsibility. What we study, we affect, however carefully, however minimally. Our presence leaves traces. Those traces will persist. In the ice, in the water, in the microbial communities that have evolved in isolation. Whether they persist as contamination or as documentation depends on choices we make. The silence does not judge those choices. It simply absorbs them, adds them to the record, continues its patient existence regardless of what we do. That indifference is clarifying. It strips away pretense, removes the illusion that our concerns are central, shows clearly that we are guests in a system that does not require guests. The question becomes, how do we behave as guests? With respect, with caution, with awareness that what we touch is older and larger than ourselves. The subglacial ocean beneath Antarctica holds no answers to those questions. It only raises them. Through its silence, through its persistence, through its vast, hidden presence. And in raising them, it reminds us why exploration matters. Not to conquer, not to claim, but to understand our place within systems we did not create and cannot control. Let us turn now to what this all means. For the future, for the planet, for the choices ahead. The future of Antarctica's subglacial ocean is being written now. In the flow rates that are increasing, in the temperatures that are rising, in the connections that are forming between previously isolated systems. What happens next depends partly on physics, on how fast the planet warms, on how ocean currents shift, on feedback loops that are already in motion. But it also depends on choices, on what we measure, on what we protect, on how seriously we take the warnings present in the data. The subglacial ocean is responding to changes that began decades ago. The warmth reaching the base of the ice sheet today comes from heat trapped in the atmosphere years earlier. The lag time is significant. This means that even if warming stopped immediately, the ice would continue responding. For years, for decades, the momentum is already built into the system. But warming is not stopping. It is continuing, accelerating in some regions, creating conditions the ice sheet has not experienced in millions of years. The question is not whether the subglacial ocean will change. It is already changing. The question is how fast, and how much of the ice sheet will respond. Current projections suggest continued retreat of major glaciers, thinning of ice shelves, acceleration of ice flow. These are not catastrophic scenarios. They are baseline expectations. The uncertainty lies in timing and magnitude. Whether changes occur over a century or 3 centuries. Whether sea level rise reaches 1 meter or 3 meters by 2100. Those differences matter enormously for adaptation, for coastal planning, for populations that will need to relocate. The subglacial hydrology is central to those projections because it controls how fast ice can slide, how quickly glaciers can respond to warming, how stable the grounding lines remain. Understanding the hidden rivers and lakes is not academic anymore. It is practical, necessary for predicting what comes next. Scientists are working to improve the models, to incorporate better data on subglacial water flow, to simulate how the system responds to different warming scenarios. But models have limits. They cannot capture every variable. They cannot predict every feedback. They give probabilities rather than certainties. The future remains probabilistic. Multiple pathways are possible. The one that unfolds depends on variables that are still changing. What is certain is that the subglacial ocean will continue to exist, even if the ice above it changes dramatically. Water will persist beneath whatever ice remains, flowing through channels, pooling in basins, shaping the continent from below. The ecosystems in that water may change. Species may go extinct as isolation ends. New organisms may arrive as systems connect. The microbial communities that evolved in darkness may face competition. Competition from surface life. That transition will happen gradually. But it will happen. The ancient separation between subglacial and surface environments is ending. For researchers, this creates urgency. To document what exists before it changes. To understand the baseline before it shifts. To collect data that future scientists will need. To interpret changes they observe. The window for studying pristine subglacial ecosystems is closing. Not immediately, but measurably. Each year that passes brings the systems closer to connection with the surface. That does not mean study should stop. It means priorities must be clear. Focus on questions that matter, on measurements that will remain relevant, on samples that capture a moment in transition. The future also involves technology. Better instruments, more sensitive sensors, autonomous vehicles that can explore beneath the ice without human guidance. These technologies are being developed, tested in Antarctic conditions, refined based on lessons from previous failures. Each generation improves on the last. Eventually, instruments may be able to map the entire subglacial network, to track water movement in real time, to monitor microbial populations without disturbing them. That capability would transform understanding, from snapshots to continuous monitoring, from isolated samples to comprehensive datasets. But technology alone is not enough. It must be guided by questions that matter, by awareness of what we risk losing, by ethical frameworks that balance discovery with preservation. The future of subglacial research involves those frameworks. Discussions about what should be studied, what should be left alone, how to minimize impact while maximizing knowledge. These are not easy questions. Different researchers have different perspectives, different priorities, different assessments of risk versus reward. But the conversations are happening at conferences, in journals, among teams planning expeditions. The community is thinking carefully about what comes next. One possibility is increased international cooperation, sharing data more openly, coordinating research to avoid duplication, pooling resources to tackle questions no single nation can answer alone. Antarctica is governed by treaty. It belongs to no one. Research there is supposed to be collaborative. The subglacial ocean offers an opportunity to make that ideal more real, because the questions it raises affect everyone. The sea level rise it contributes to does not respect borders. The climate feedbacks it triggers are global. The life it harbors informs searches for life beyond Earth. The future involves recognizing those connections, acting on them, making decisions that reflect shared interest rather than national competition. Another aspect of the future involves communication, helping people understand why the subglacial ocean matters, why research there is worth supporting, why protecting it is in everyone's interest. That communication is challenging. The subglacial world is invisible, difficult to visualize, hard to connect to daily life. But the connections exist through sea level, through climate, through the simple fact that what happens beneath Antarctica's ice eventually affects coastlines everywhere. Making those connections clear is part of the work. Not just collecting data, but translating it, making it accessible, helping others see what researchers see. The future is not predetermined. Choices still matter. Investments in research matter. Policies that reduce warming matter. International cooperation matters. The subglacial ocean will respond to what we do. Not immediately, but inevitably. The physics does not care about intention, only about energy. If we reduce the energy entering the system, the ice responds more slowly. If we continue adding energy, it responds faster. The relationship is clear. What comes next depends on recognizing that relationship, on accepting that the subglacial ocean is not separate. It is connected, part of a system that includes atmosphere, oceans, ice, and everything that depends on those elements remaining in balance. The future of Antarctica's hidden water is the future of the planet's coasts, of its climate, of the species that depend on both. It is being written now, in the flow of water beneath the ice, in the measurements scientists collect, in the decisions societies make about energy and climate. The subglacial ocean does not care what we decide. It will respond according to physics, flowing faster if conditions allow, slowing if they do not, existing either way. But we are part of those conditions. We influence them, and therefore we influence what comes next, whether we intend to or not. That responsibility is part of what studying the subglacial ocean teaches. That observation is never neutral. That measurement always has context. That knowledge carries obligation. The future is uncertain, but not unknowable, not unpredictable in broad strokes. The direction is clear. The rate is what remains to be determined. And that rate depends partly on what happens next. In laboratories, in policy discussions, in the choices made by nations and individuals, about how seriously to take the signals coming from beneath the ice. Signals that say, I am changing. I am responding. I am connected to everything you depend on. Pay attention. The question is whether we will, and what we will do with that attention if we offer it. There is water moving in darkness right now. It flows beneath ice that may never melt, through channels that may never see light, carrying chemistry that evolved when the world was unrecognizably different. That water is not aware of us. It does not know it is being studied. It simply exists, following the paths that pressure and gravity provide, shaping the continent in ways too slow for human perception. But it remembers, not through consciousness, but through chemistry, through isotopes that record climate, through dissolved gases that trace ancient atmospheres, through microbes that carry genetic history spanning millions of years. The subglacial ocean is memory, planetary memory, stored in liquid form, protected by ice from the changes that rewrote the surface world. When we sample that water, we are reading those memories, learning what the planet was, how it changed, what persisted when everything else transformed. Those lessons are not comfortable. They show that stability is temporary, that ice sheets grow and shrink, that sea levels rise and fall, that nothing about our current climate is permanent. But they also show resilience, that life adapts, that water finds paths, that systems persist even through massive change, just in different forms. Antarctica's subglacial ocean has survived ice ages, warm periods, continental drift, impacts from space. It has outlasted species, outlasted ecosystems, outlasted civilizations that never knew it existed. It will outlast us too, in some form, whether as isolated lakes beneath remaining ice, or as part of the modern ocean if the ice melts away. Water persists. The chemistry continues. What we choose matters for how that persistence unfolds, for how fast, for how disruptively, for what else survives alongside the water. But the choice to matter is itself a choice. To recognize connection, to accept responsibility, to act on knowledge rather than ignore it. The subglacial ocean asks nothing, but it offers everything. Lessons about time, about change, about what endures when conditions shift. Those lessons are available, recorded in the water, encoded in the ice, waiting in the darkness for anyone patient enough to listen. The listening is difficult. It requires instruments that can sense what eyes cannot see, models that can interpret what intuition cannot grasp, patience that can wait for answers that arrive slowly. But the listening is possible and necessary, because what the subglacial ocean has to say is important, not just for science, for everyone who depends on stable coastlines, on predictable climate, on oceans that support life. The water beneath Antarctica is connected to all of that, through physics that does not care about borders, through chemistry that affects atmosphere and ocean everywhere, through ice that holds enough volume to reshape continents. Ignoring it does not make it irrelevant. Dismissing it does not make it disappear. It continues regardless, responding to forces we influence whether we acknowledge it or not. The question is whether we will engage with that reality, or whether we will let it unfold without our input. Reactive rather than responsive, surprised rather than prepared. The data suggests preparation is better. That understanding what comes next allows adaptation. That knowing which glaciers will fail first helps determine where to invest in protection. The subglacial ocean can inform those decisions through continued study, through improved models, through instruments that track changes as they occur. But only if we choose to support that work, to value knowledge about invisible processes, to invest in understanding systems that operate beyond human timescales. The choice is not dramatic. It is practical, mundane even, funding research, supporting international cooperation, maintaining instrument networks, analyzing data carefully. But those mundane choices accumulate. They determine whether we face the future with information or ignorance, with preparation or surprise, with adaptation or crisis. The subglacial ocean does not care which we choose. It will exist either way, flowing in darkness, responding to physics, continuing its patient circulation. But we should care, because the consequences of its changes will reach every coastline, every community built near water, every system that depends on climate remaining within certain bounds. The ocean beneath Antarctica is not separate. It is part of the whole, part of the same system that creates weather, that drives currents, that supports life. Understanding it is understanding ourselves, our vulnerability, our connection, our place within processes larger than civilization. That understanding is not comfortable, but it is honest. And honesty is the foundation for response that matters. The subglacial ocean will keep flowing. The ice will keep changing. The planet will keep responding to energy we add to its systems. What we do next is the only variable still open, the only part of the future not yet written in physics. The water in the darkness does not judge our choices. It simply reflects them, through the rate at which it flows, the speed at which it warms, the consequences that follow from both. In the end, Antarctica's subglacial ocean remains unsolved. Not because research has failed, but because complexity exceeds any single solution. It is a system, dynamic, interconnected, responding to forces from every direction. It cannot be reduced to simple explanation, cannot be captured in single measurements, but it can be approached, studied, understood partially, and that partial understanding is valuable, essential even, because the alternative is blindness, moving into a changing future without knowledge of what drives that change, without awareness of what feedbacks are already in motion. The subglacial ocean offers sight, through data, through models, through the patient work of researchers who return year after year to listen to ice and water. That sight is not perfect, but it is better than darkness, better than assumption, better than hoping the changes will be slow enough to ignore. The water beneath Antarctica is moving, rising, connecting, transforming from ancient isolation to modern integration. That transformation will shape the world. Slowly, but inevitably. The ocean remembers what the planet was, and it is showing us what it might become. If we listen, if we measure, if we accept what the silence beneath the ice is trying to tell us, that we are temporary, that systems are interconnected, that change is constant, and that understanding, however incomplete, is always better than ignorance. The subglacial ocean flows, in darkness, in silence, in patient response to forces beyond control. It will continue, long after our questions fade, long after our instruments fail, long after the last measurement is recorded. It is the planet's own memory. Deep, cold, persistent, waiting for nothing, simply existing in the dark. And in that existence, it holds everything we need to know about time, about change, about what survives when everything else transforms. The lesson is simple. Nothing is permanent, but some things persist, in different forms, through different pathways, carrying forward what matters across time that makes human history seem brief. The subglacial ocean is one of those things. Memory in motion, history in liquid form, the planet talking to itself in a language older than words. We have learned to translate fragments, enough to know the conversation is important, enough to recognize we are part of what is being discussed. Whether we continue listening is our choice, but the conversation continues either way. Beneath the ice, in the darkness, where water remembers everything.